Hello and welcome to EP3O04 test number 11 prep. Okay, so we're going to look at the test number 11 from 2016, and this is on heat exchangers. So first question, in a thin wall, parallel flow heat exchanger, hot fluid enters the heat exchanger at a temperature of 150 C and a mass flow rate of 3 kilograms a second. Cooling fluid enters the heat exchanger at a temperature of 30 degrees with a mass flow rate of 2 and leaves at a temperature of 50. The specific heat capacities of the hot and cold fluids are here. The convection heat transfer coefficients on the inner and outer side of the tube are these, and we have fouling factors given on the inner and outer side of the tube. So on the tube side and then on the shell side, that's the inside and the outside. Determine the overall heat transfer coefficient, the exit temperature of the hot fluid, and the surface area of the heat exchanger using the LMTD method. All right, so the overall heat transfer coefficient is this U parameter, where in terms of fouling factors, we have a full formula here. So the idea is that 1 over UAS is equal to the total resistance, which is equal to the sum of all of these different parameters there. So we can go back over there and then say, okay, now for a thin-walled heat exchanger, the areas are all the same. So that means that we can cancel out the areas in these formulas, and the wall resistance itself is equal to 0. So maybe we'll put in a 0 there and then get rid of the area by multiplying everything by AS, by the surface area. Since we don't know the surface area, this is a pretty convenient thing to do. So what we're left with is that the overall heat transfer coefficient is 1 over this sum over here in terms of all those parameters that we were given. So that's not so bad. We can figure that out. So U should be equal to 1 over 300 plus 1 over 600 plus 3e minus 4 plus 1e minus 4. For an overall heat transfer coefficient of 185. This should be lower than the convection coefficients that we started with in order to get it. Next part asks us to find the exit temperature of the hot fluid, and this is the kind of problem where we actually know enough about the fluid exiting conditions to be able to figure that out from an energy balance. So to kind of summarize where that information comes from, that's in 22.3. The idea is that the rate of heat entering the cold fluid equals the rate of heat leaving the hot fluid, and each of these can be figured out from the heat capacity rates times the difference in temperatures. So if we take that piece of information and put that in there just to continue summarizing the theory, we are going to need to write down these temperatures that we've got. So we've got T hot in and M dot hot, which is 3. We've got TCI, the cold fluid entering temperature, is 30, and the cold fluid mass flow rate is 2. And then this is the part that makes all the difference. We've got TC exit as 50, so we know that, and that means that we can figure out Q dot is equal to, also we need to know the heat capacities, right? So CPH is 1150 and CPC is 4180. So because of that, now we've got the ability to calculate the total energy transfer rate, the rate of energy transfer from the hot fluid to the cold fluid by the rate that the cold fluid is increasing in temperature, and that would be its mass flow rate times its heat capacity times the increase in temperature that it has. So that should be the total rate of energy transfer. Then once we now that we have that, we can solve for what the exit temperature of the hot fluid is. So the exit temperature of the hot fluid would be its entrance temperature, its inlet temperature, minus that energy transfer rate divided by the mass flow rate for the hot fluid times its heat capacity. Okay, let's just turn that into a floating point. Oh, wrong heat capacity. Yeah, something looked off about that. Okay, so the hot fluid exit temperature is 101.5, and we can do that just from an energy balance. So we didn't have to use anything really about the heat exchanger like the LMTD method or anything yet, but we are going to use that for the third part, the surface area of the heat exchanger. So the idea is that the surface area is related to the overall heat transfer coefficient and the change in temperature from the hot side to the cold side at any point to give you the rate of energy transfer. So this is kind of like, if you think UAS is 1 over the thermal resistance, then this is kind of like I equals V over R for an appropriate change in voltage and resistance. So the problem is that the temperature difference isn't the same all the way across. So you remember this from the intro to heat exchangers here. For a parallel flow, we've got a change in the temperature difference. And even for a counterflow, if everything isn't completely symmetric in terms of heat capacity rates, then you're going to have a difference in the temperature difference as you move across it. So which temperature difference do you use? Well, the log mean temperature difference accounts for that. So this is, again, a temperature difference between the hot side and the cold side, and you evaluate it using one of these delta T's at the difference in temperature at the output and the other one at the difference in temperature at the input. So then we've got LMTD is going to be T. So let's actually write out what these delta T's are. DT exit, or maybe we'll call it like DT1. Yeah, so that's going to be the bigger one for us to get a positive number here. So DT1 should be at the inlet, so that's THI minus TCI for parallel flow, and DT2 is THE minus TCE. If it was a counterflow, you would use a different you'd use a different set of parameters. So it's kind of like the hot in minus the cold out rather than the cold in. The idea is you use the temperature difference at each side of this thing. In either case, that's what's consistent between the two different methods there. So continuing, LMTD would be DT1 minus DT2 over ln of DT1 over DT2. And we find a log mean temperature difference of 81. Now, just as a check, this should be kind of like the average temperature difference. But for parallel flow, it should be slightly lower than that, or at least somewhat lower, because it represents the fact that the heat exchanger spends more time near having had the temperature change already. So because of this exponential approach in this kind of heat exchanger, you've got more time at this lower temperature difference. So it's not as much temperature difference that as you would get if you were to just average the total difference. That would be kind of assuming that we have a straight line. And you see from this this curved approach here, this exponential approach, we have less temperature difference than we would have gotten through that straight line. Like the straight line fits from here to there, and there to there would have a larger difference on average than these ones. Okay. So that's the LMTD. And then what do we do with that? Well, we say that Q dot is UAS times LMTD, which means the surface area, since we have U and we have Q dot and we have delta T ln, is Q dot over LMTD times U. And there we go. So we need a surface area of 11.1 square meters. Question 2 says, in a 1 shell pass and 2 tube pass heat exchanger, cold water with an inlet temperature of this is heated by hot water supplied at the inlet at this. The cold and hot water flow rates are this and this. If the shell and tube heat exchanger has UAS of that, figure out the cold water and hot water outlet temperatures. Assume these heat capacities. Okay, so this is a pretty different problem from the previous one you may have noticed that they give you UAS at the start, whereas last time we didn't know the surface area. And the critical thing is that now we don't have any of the exit conditions, so we can't use the energy balance equations that we did last time to figure out the exit temperatures and the total heat transfer rate. So while all of these equations are still true, they're not as useful as they were before, since this equation is going to have, yes, we know this, but we have this unknown and this unknown. Now from the series of these other equations, sure, we know the inlet conditions in each of these, so we sort of have 1, 2, 3 equations and 3 unknowns, and in principle we can solve it, but the log mean temperature difference is so coupled in things that this is difficult to use. Plus, the log mean temperature difference that we calculated for a pure parallel or counterflow going to be working exactly the same for this kind of a heat exchanger? Fair question. Okay, so rather than go about it that way, we're going to use the Effectiveness Ntu method. Let's just overview exactly how that's going to work. So the effectiveness is defined as the actual heat transfer rate over the max possible heat transfer rate. This would be figured out by the difference in the inlet temperatures times the minimum of the heat capacity rates. The idea is if you had a pure counterflow heat exchanger and you let it go long enough, eventually one of the fluids would go to the inlet temperature of the other one. So in counterflow, if the cold fluid has more heat capacity rate than the hot fluid, then the hot fluid could get basically to the temperature of the cold fluid, but by that point the energy that it has transferred to the cold fluid wouldn't be enough to bring the cold fluid up to the hot fluid's temperature, since in that hypothetical example the cold fluid has a higher heat capacity rate. So for the hot fluid to have the maximum possible temperature difference, second law guarantees that we can't have the hot fluid leaving at a lower temperature than the cold fluid entered at. We can't have enough heat transfer rate here to give the same temperature difference, right? If this heat capacity rate is higher, then this temperature difference has to be lower than over here. So the maximum possible one you could get is based on the difference in the inlet temperatures and the minimum of the heat capacity rates. Okay, so once you've got that, there's some formulas for effectiveness in terms of the number of transfer units defined as UAS over the minimum of the heat capacity rates. And we have a nice table here that tells you for 1 shell pass and N tube passes. So 2, 4, 6, 8, etc. So what we're going to need to do then is figure out the minimum heat capacity rate, the ratio of that to the maximum one, and then the NTU, then substitute into this formula to get the effectiveness, and then calculate the actual heat transfer rate from multiplying that by Q dot max, and then go about using that to figure out the exit temperatures of the cold and the hot fluids. Okay, so let's go. We've got cold water comes in at 20, hot water comes in at 80, and m dot k is equal to 3, m doth is equal to 2, CPC is 4178, CPH is 4188. Then UAS is 11600. The CC is equal to CPC times m dot k, and the hot fluid heat capacity rate is m doth, I guess, times CPH. So the hot fluid has a lower heat capacity rate, which means that the Q dot max is equal to THI minus TCI times CH. Okay, then the NTU is equal to UAS divided by CH, and So that's about 1.4 transfer units. The C parameter is CH over CC. So now that we've got that, we can go and figure out the effectiveness from this table. And this is quite a challenge, all things considered. Or at least some things considered, perhaps. It's kind of difficult to substitute into this formula because of the number of parameters there, so it's a bit challenging to even type it out. So let's give it a shot anyway. Gotta rearrange things to fit it all on one page. Then we'll say effectiveness is 2 divided by 1 plus c plus square root 1 plus c squared times, and we're going to have something over something else. And the first thing is 1 plus e to the negative NTU times the square root of 1 plus c squared. And the second thing, let's just check that this is right. 1 plus e to the negative NTU square root 1 plus c squared. Okay. And the second thing in the denominator there is the same thing, but with a negative. And because we're dividing by this whole thing, that accounts for the to the power of -1 and all of that. So that should be working out. Looks like it's all good. Suppose we need an eval around that. Okay, so effectiveness of about 58%. And now that we've got that, we can figure out the actual Q dot by multiplying the effectiveness by Q dot max. And so that's a lower heat transfer rate than the maximum one, makes sense. And we can figure out the exit temperatures now. TH exit would be equal to TH inlet minus the actual Q dot over the hot fluid heat capacity rate. And similarly, the cold fluid exit should be TCI plus Q dot over CC. So this tells us that in this particular case, the hot fluid has exited at 45 and the cold fluid has exited at 43. What could you do to make this better? Well, you could increase the number of transfer units by increasing UAS. So we could go from here up to, twice as long, and let's see how much better it gets. Yeah, so now because the shell and tube passes kind of counterflow in its nature, this means the exit temperature of the hot fluid has gone down below the exit temperature of the cold fluid. Okay, so that's it. Thanks for watching.